Okay, so that's vertical asymptotes. We're going to move on and look at horizontal and oblique asymptotes. And there's two possibilities when you're looking at horizontal and oblique asymptotes. So we kind of work these problems two different ways, and it depends on whether the rational function is proper or improper. So first, let's define proper and improper, and then from that we'll look at how to find horizontal and oblique asymptotes for these rational functions. So when we talk about proper or improper rational functions, that has everything to do with the degree of the two polynomials in that function. The two polynomials being the numerator and the denominator of that function. So if it's proper, that means the degree of the numerator is less than the degree of the denominator. So just as an example, going back here, we'll just look at these examples. Part B here is proper. The numerator's degree is 1. The denominator's degree is 2. So this is proper. Okay. We can't say the same for C. Here the degree is 2. The denominator's degree is 2. Right, both have the x squareds. So this would be improper. Okay, the numerator's degree is less than the denominator's degree. It's proper, otherwise it's improper. And so what does that have to do with horizontal and oblique asymptotes? Well, if it's proper, then y equals 0 is the horizontal asymptote of the graph. And remember, when we talked about horizontal and oblique asymptotes, we said there's always just one of those. So if you have a horizontal asymptote, you do not have an oblique asymptote, and vice versa. You can also have neither. We'll see cases of that as well. But if it's proper, y equals 0 is a horizontal asymptote. And so example 5 here says find the horizontal asymptote on the graph of this rational function x minus 12 over 4x squared plus x plus 1. And so for that, again, we first decide if this thing is proper or improper. Well, the numerator's degree is, the numerator's degree is 1. Denominator's degree is 2, so that is proper, which means y equals 0 is the horizontal asymptote. Okay, so that's all there is to it. If it's proper, automatically know y equals 0 is a horizontal asymptote. Again, well, let's just quickly punch this in here and look at the graph. X minus 12 divided by 4x squared plus x plus 1. And what you want to see, the line y equals 0 is the x-axis. Okay, that's that horizontal line right here. And if I turn off the axes, you can kind of see that whole graph now. Remember, x-axis was right here. Notice that graph flattens out at the x-axis. Okay, and so that checks out. That y equals 0 is the horizontal asymptote there. Okay. So, of course, that brings up the question, well, what if it's improper, right? So how do we go about figuring this out, finding horizontal or oblique asymptotes if the rational function is improper? And so to do that, we've got to do a little bit of work. Of course, it can't be as easy as the other one, right? So what we need to do is use long division. So we use polynomial long division to rewrite our function, and And once we do that, there's kind of three possibilities. We either come up with a horizontal asymptote, an oblique asymptote, or neither. It could be the case that there are neither of those. Okay, so what's this long division we're looking at? How does that work? Okay, so let me set this up just using an example, and then I'll show you how we come up with the answer as far as the asymptotes go. So here we've got a rational function. This one is improper. This is a 4th degree divided by a 3rd degree polynomial, so that is improper. And we want to set this up using long division. Okay, so the way that works, you divide the denominator into the numerator. And when you set this up for the numerator, you have to put placeholders in for the missing powers of x. So like I've got x to the 4th, I don't have an x cubed term up here, so I'm going to put in just a placeholder 0x cubed and then minus x squared. And we can go ahead and let's just do plus 0x plus 0. Okay, so placeholders for all the missing powers of x. If you start out with a 3x to the 4th, you need to have an x cubed, an x squared, an x, and a constant term. And so that's the setup. If you leave out one of these placeholder terms, it's going to mess you up. Okay, so you got to make sure you get that set up properly to begin with. From here, we say, okay, x cubed times what? Starting with always with this first term here, x cubed times what would give us 3x to the 4th. So if I multiply x cubed by 3x, and actually I need to put that, keep this organized here. If I multiply it by 3x, then that will give me 3x to the 4th, right? X cubed times 3x is 3x to the 4th. And notice I put that 3x on top of my x column. So we kind of keep all this orderly and arranged here. Now I'm going to multiply back through. So 3x, kind of distribute this to all three of those. 3x times x cubed is 3x to the 4th. 3x times negative x squared is minus 3x cubed. 3x times 1 is 3x. So multiply back through, keeping everything lined up in the columns. And then the next step when you're doing long division is to subtract. Now when you subtract here, you got to be careful because what we're doing is we're subtracting all of these terms. So 3x to the 4th minus 3x to the 4th is going to cancel out. 0 minus negative 3 is a positive 3x cubed. You can just bring down the minus x squared. 0 minus 3 is minus 3x. And then just bring down the 0. Okay. So that's the first round of long division, and we just repeat that process, comparing x cubed now to 3x cubed. You would need to multiply x cubed by 3 to get 3x cubed. Again, we're going to distribute back through. This time using the 3. 3 times x cubed is 3x cubed. 3 times minus x squared is minus 3x squared. 3 times 1 is 3. And subtract. And I end up with these canceling. Minus x squared minus negative 3. So if I have minus x squared minus negative 3x squared, make sure you get all those negative signs in there. That ends up being a plus 3x squared, so that's a 2x squared. Bring down the minus 3x. 0 minus 3 is negative 3. All right, now at this point we're actually done. And the way that I know that we're done with what we're doing here is two things. First of all, this term right here, 2x squared, its power is less than this term up here I'm comparing with, x cubed. So at that point, I'm done. Also, if you'll notice up here, for this part, I hit a constant term. Okay, once you get a constant term there, that's as far as you're going to go as well. And so that's the long division piece. It's a lot of work as far as, well, it's once you get the process down, it's not too bad, but there's a lot of room for small mistakes, little negative sign errors and things like that. So just take your time with it, be careful. So we did all that. Now what's the result? What are we even trying to do? We're trying to find horizontal or oblique asymptotes, right? And the result is actually what I've got written in blue here, this piece. Okay, 3x plus 3. If I look at 3x plus 3, what kind of equation is that? That's a linear equation, right? That's a line having slope of 3, right? 3x. And we would call that an oblique asymptote. How do I know that's oblique? Okay, if we go back to these notes here, the three possibilities, the second one, oblique asymptote, if that f of x, what we're referring to as f of x, is what I had written in blue there. If it's a linear equation, ax plus b, or mx plus b, you can think of it that way as well, then we call that an oblique asymptote. So 3x plus 3. And we're done. We got our answer. And you can verify this as well. You can actually check your work with a graph. You need to graph both the original function. So let me get that plugged in. 3x to the fourth plus, minus x squared. Then it's x cubed minus x squared plus 1. So I'm going to graph my original function. I'm also going to graph 3x plus 3, that oblique asymptote. Okay, and what I'm going to do, I'm going to change the way that that graph is drawn. I'm going to make it something where we can kind of make it stand out. So here's what we got. So here is the original graph. Here's that rational function. And then here's the oblique asymptote. It's kind of a mess. So let's fix our window. It looks like most all this stuff's happening between like -3 and +3 on those x values. So let me just maybe do that. See if that makes it any easier to see. Okay, so what you need to get from this, what you're looking for is that the oblique asymptote, that line that's getting drawn in there, that's what the ends of the graph approach. Okay, and so you can see that the left side of the graph, excuse me, and the right side of the graph start to flatten out and basically line right up with that 3x plus 3. So I know that that is the correct answer. Now, how do you know if you got something that's not correct? Well, if I change that to like, let's say 5x plus 3, for some reason maybe we got that as an answer. You'll notice that it doesn't fit in with the ends of the graph very well. See how it's set up to where it's not really approaching the ends of the graph. You know, these two pieces right here and right here are actually getting further away from each other. Okay, so those should come together and get closer and closer the further out the ends of the graph go. So that's an oblique asymptote. That's how that works. Let's do another example. 8x squared minus x plus 2 over 4x squared minus 1. In this case, this is improper, right? This is a second degree divided by a second degree, so that's improper. So we need to do our long division. So let me set this up. 4x squared minus 1. I'm dividing into that numerator, 8x squared. Notice there's no missing terms. Minus x plus 2. No terms missing there. So we can just use what's given to us. We're going to compare those two terms there. Say, all right, what do I need to multiply 4x squared by to get 8x squared? How about a 2? Now, if you're real quick about this and are paying attention and know what we're looking for in our answer, you should remember that all this stuff down here really doesn't matter as you're working out that long division when you get to the end. I mean, what matters is what's up here, right? And earlier, if you'll remember, I said that once you get a constant term up there, you're done. So that means for this, we're done. Okay, so 2 is our answer. We just need to classify that. Is that a horizontal asymptote, an oblique asymptote, or is that neither? Okay, going back to our notes, if we get a constant term, that top piece is just a single number, that's a horizontal asymptote. So y equals 2 is a horizontal asymptote. And again, you can verify that. You guys are probably getting tired of me graphing all these, but I think it's useful here to see the picture and understand what we're dealing with. 8x squared minus x plus 2 divided by 4x squared minus 1. Here's my original function, and then my y equal to asymptote. You can notice the ends of the graph, the far left side and the far right side, once it gets over there, do start to line up with that horizontal asymptote. So that's exactly what we're expecting to see. It's exactly what we're looking for. Okay, last question. So again, this is improper. This is a 5th degree divided by a 3rd degree. So improper. So let's set up our division. X cubed minus 1. And we're dividing into 2x to the 5th. Missing an x to the 4th term. So let's put a placeholder, 0x to the 4th. Minus x cubed. We're missing an x squared. We're also missing an we're also missing an x term. And then our plus 2. So let's kick this thing off again, starting with comparing x cubed to 2x to the 5th. You need to multiply x cubed by a 2x squared to get 2x to the 5th. Now, I'm going to give you a good shortcut here. As you're looking for horizontal and oblique asymptotes and you're doing this long division, remember what we said about horizontal asymptotes? Horizontal asymptotes are of the form y equals like b, or let's say y equals some constant, like the last one we got was y equal 2. Well, that was a horizontal. We said oblique would be like a linear. Earlier we got 3x plus 3. Now, do either of those have an x squared? 2 or 3x plus 3? No, there's no squared x term. And as a matter of fact, horizontal asymptotes will always just be a constant. Oblique asymptotes will always be linear, which means they'll always just have an x term. So if we get something that's got a higher power of x, like a 2x squared, that's not either one of those, right? So from that we could say neither. we know right away if we get a higher power of x, an x squared or an x cubed, something like that, that it's not going to be an oblique or a horizontal asymptote. And we can stop right there. Now that kind of leaves you wondering, well, what would the asymptote be then? What does it look like? What do the ends of the graph do? So let's graph this thing real quick and see what does that look like. So 2x to the 5th minus x cubed plus 2 divided by, whoa, let me back up. Make sure you don't stay in that exponent there. Plus 2 divided by x cubed minus 1. And I'm going to reset my window here. And I get a picture something like this. Okay, and let me actually kind of switch my window around a little bit so we can get a better idea of what's happening here. What we actually have is the ends of the graph are approaching a parabola. Okay, there's like a U shape here that the ends of the graph are approaching. Can you see that? That's why it's not horizontal or oblique, because it's actually like a squared, x squared sort of graph that the ends are approaching. We don't classify that, we just say neither. And that's the end of 5.2, so if you have questions on that, let me know.